Okay, so this is a very interesting problem. Here we'll be using physics and a little bit of geometry to solve this problem. So first of all, we have two mics, um, and then we have a microphone over here, and we have two speakers and one microphone over here, and what is given is they're 3 meters apart, and then from midpoint to the microphone it's 3.2 meters, and then we have the distance between them. Now so it says that the microphone, they're in phase, and they emit 474 hertz sound. So yeah, so they're in phase and they're emitting 474 hertz of sound. Now the thing is, we should write that as loudspeaker or not mic. So let's say that's speaker 1, and then this is speaker 2. So if they're in phase, if we look at their wave pattern, we see to be in phase, their maxima and minima should be matching with each other, and that's what we're seeing. We see a node over here which is same as here, and then they have the same maxima at the same side. Now the question is, how far must the microphone be moved to right to find the first intensity minimum? Now what we're doing is we're moving this microphone. Now if we want to find the first intensity minimum, we see that it needs to go half of the wavelength, because I mean, if the microphone is around, let's say, this region, they have this maximum value, and then it needs to go around this point where they don't have the maxima. So this is the node, and then yeah, that's the minima. So it's like half of the wavelength. So we do that. So yeah, so what's happening here is we have this intensity maxima around this region, and then they are the nodes are matching over here, which is the minima. So the gap is half of the wavelength, and we'll try. And if we look at the geometry, so what we did here is our microphone is now here, which was initially there here, which is the midpoint. So the relation that we're concerned here is, now we have two different distances, d1 and d2, and the difference between their distance should be matching with half of the wavelength. So that's what we did here. So D2 is clearly greater than D1. So at this moment, we should not bother about the numbers. Let's look at the geometry and try to solve for it. So we're trying to solve for this X. We are trying to find how far the microphone moved. So yeah, let's try to solve it using the letters, and then we'll plug in the numbers. Right. So yeah, as we said, d2 minus d1 is half of the wavelength. Now, what's d2 and what's d1? Let's try to find out. So, the distance from this microphone to the midpoint of the speakers is L, and the distance between the mics is D. So what's happening is d2 is basically, we'll be using Pythagorean theorem, and to get that we need this distance and this much distance. So we know that this whole thing is D, and this is the midpoint, so that's half of D. So let's see, this right here is half of D, and then we have this extra x over here. So if we add that part, so that's x. So this distance right here, this is half of d plus x. That's what we have here. And this distance is L, so that's L. So what Pythagorean theorem tells us is the square of this term should be equal to the square of this term plus this term, right? Let me write that down. So let's say you have a triangle and the ax the distance between this point is A, the distance between this and that is B, and this is C. So the theorem tells us that C square should be equal to, and of course A and B must be perpendicular to each other. So C square must be equal to A squared plus B squared. And in other words, C is square root of A squared plus B squared. So that's what is done here. So we found the distance, and from this point to that point and from this point to this point, and we applied Pythagorean theorem to replace d2. Similarly, the distance from here to here is nothing but half of d minus this x extra term, and that's what we got here. And then again we're applying Pythagorean theorem to get d1. So all we did was we replaced our d2 and d1, and then we need to, so what we did was we need to square it, we need to get rid of this square root term, and to do so we are taking this term on the right on this side, and that's how we are getting rid of this negative sign, so it becomes positive when it's on the right. And then we're taking square on both sides, and then we end up having this whole big expression. Now what we did here is a formula that we use very commonly in maths. So if you have a squared plus b squared, we write that as, sorry, if we have a plus b whole squared, we write that as a squared plus 2ab plus b squared. And that's what we did here. When we took the square on both sides, um, this term is our a, this term is our b. See, let me mark those. So this term is b, this term is a. So we're taking a squared plus b squared, and so that's our a squared, this guy is our b squared, and in between we have 2 times a times b. So yeah, and once we did that, we can get rid of this L square on both sides, and then we have this expression. Now we're using another common formula in this problem, which is a plus b whole squared minus a minus b whole squared gives us gives us 4 times ab, right? um, so that's what's happening here. So we have now we have a and we have b, we have a and we have b. So we're taking this guy on the left, and that makes this expression, and then we're replacing this whole big expression by simply writing 4 times this first term and second term. So that's what's happening here. So that's 4 times half of d times x, that gives us 2 dx. And then we're taking this guy on left, so that's why we have a negative sign. And then again we have a square root term, right? So as you can see, if we have a square root, we need to get rid of that because we're solving for x. So we take square again, and if we do so, we have this big expression now. So now all we're doing is we're simplifying this expression. Now it's a very big expression, but I would suggest everyone to do it on their own so that um, you get used to this lengthy calculation. But it's it needs some practice to get accustomed to it. But yeah, so we have this big expression now, and then we're solving for x. So if we take x on one side and then solve for it, we get this expression. Now let's put the values. So d is the distance between the speakers. So d is 3 meters. Then L is the distance from your microphone, our microphone, to the midpoint of the speaker, which is 3.2 meters. And lambda is the wavelength, which is speed of sound over the frequency. So the frequency is given, which is 474 hertz, and the speed of sound at 20 degrees Celsius is 343. So if we put that, we get our lambda as 0.736. Now you should put all the numbers over here, and you should be getting x as 0.429 meters. So that is the answer for part A, right? So at 0.429 meters to the right from the midpoint, we should be getting minimum intensity. Now the next part says that suppose the speakers are reconnected so that 474 hertz sounds they emit are exactly out of phase. So now what's happening is they're out of phase. So at what positions are the intensity maximum and minimum now? So now what's happening is this guy. So instead of there being in phase, now they're out of phase. So if they're out of phase and then we need to get our minima and maxima, so all we gotta do is we shift this. So like if we shift this whole part on the right or on the left, we get back this wavelength, right? Because um, the wavelength that is generated is like that. So it goes on. And similarly for the other speaker as well. So yeah, if we shift this part to the left or to the right, we get back this wavelength, right? So that means when exactly out of phase, the maxima and minima will be interchanged, right? So that's why the intensity maxima will now be at 0.49 meter to the left or to the right of the midpoint, because as we explained that we can move it to the left or right and we'll get this wavelength back. So yeah, so that's why the maxima will be 0.429 meters to the left or right of the midpoint, and the minima will be at the midpoint because they are now out of phase. So that's where you're getting your minima. So the minima will be at the midpoint.